Now we're going to talk about the energy and power of traveling waves. This is a very important topic because a traveling wave, is really a transport of energy from one place to another. So you're transporting energy, but you're not transporting matter. We mentioned that before, that when we said that the motion is transverse, perpendicular to the actual motion of the wave, the propagation of the wave. So wave is something that can transfer energy and power from one place to another without the actual transfer of motion of the particles, of objects. Okay, so let's derive the equation for the energy of a wave. We're going to focus on the kinetic energy of the wave. The kinetic energy. So imagine that you have a piece of the string here, like this, and the wave is traveling this way, and it's bobbing up and down transverse to the motion, right? Like this. So we're going to focus on a piece here, and as it's moving up and down, we want to calculate its kinetic energy of motion, and then we'll average that out over one wavelength. We want to see how much energy one wavelength of the wave packs, okay? The kinetic energy of that piece is going to be half times its mass, the mass here dm of that piece, right? So we can call that dm times its velocity y squared. Because remember, the motion, the velocity is in the y direction, so it's moving up and down, v sub y, right? So now dm, we can call that its linear mass density mu, the mu of the string, right? The linear mass density times its length dx. V sub y, we're going to use the equation that we derived before. Remember, the general equation of a traveling wave was yx sine of kx minus vt plus phi, right? So then we're going to take that v sub y and square that. So you're going to get a squared, k squared, v squared. So I'm squaring this. So since it's negative, but when you square it, it doesn't matter, they all become positive, and then you're going to get cosine squared. Cosine squared kx minus vt. And what are we going to do? This gives us the kinetic energy. We can rewrite this as half mu a squared k squared v squared cosine squared kx. Now I can rewrite this, I can multiply this in and then say kx minus omega t. That's the other way that we can write it. And then dx, right? Now if I want to calculate this, this gives us only the kinetic energy of this piece, right? And as a function of time. Now let's focus on the snapshot of the wave. So let's say at t equals to 0, and I want to calculate the total kinetic energy of one wavelength of the wave. Okay, so let's make this easy. So make the time equal to 0, and then this one will disappear. And then I want to calculate the total kinetic energy of one wave. So I'll integrate this, because this is just the kinetic energy of this little piece. So we can call it d kinetic energy. It's a little small kinetic energy. So what would be the total kinetic energy of a wave starting here, going up, all the way down, and then back up again? So up, down, and back up, what would be the total kinetic energy packed in that one wavelength of the wave at t equal to 0? And then that's also going to stay the same because we're assuming kinetic energy and potential energy are conserved. We're assuming the wave is not dissipating, it's not losing energy. So at any value of t, that kinetic energy will stay the same, right? So, and then it's going to be the integral of cosine squared kx dx from 0 to 1 wavelength, right? And they'll give us the total kinetic energy in one wave. So how do we calculate that? Well, these kind of things appear quite a lot in physics, where we're where we're integrating cosine squared. The usual technique that we do is we use the property of trig functions. Cosine squared theta is equal to cosine of 2 theta plus 1 over 2. So that would be an easy way to integrate that, and then the integral is much easier. So then you're going to have kinetic energy. Since cosine squared is going to be 2 is going to come out, what we're going to do first is say, do u substitution. Let u equal kx du is equal to k dx, and then dx is going to be du over k. That's a, remember the k is the wave number, and then so that becomes 1/2 mu a squared k squared v squared, okay? And then you're going to have integral here 0 to, let's see, cosine squared u du, right? Dx is going to be du over k, so 1 over k is going to come out, right? And then what's going to be the new limits of the integral? So when x is lambda, u is going to equal k, and then when x is lambda, u is going to equal k lambda. So your limits of the integral are 0 to k lambda. Okay, right? And then what's the integral of that? So the kinetic energy is going to be 1/4 mu a squared k v squared. Okay, the integral of cosine of 2u is going to be sine of 2u over 2, right? Sine of 2u over 2 plus the integral of 1 is u. Then you can calculate that from 0 to k lambda. Okay, so then what happens there? Now let's erase some of the top stuff, right? And then when you put in 0, you're going to get sine of 0, which is 0. And then when you put in 0 here, you're going to get 0 also. Okay, so what is this equal to? Well, remember what k was. K was the wave number, and it was equal to 2 pi over lambda. So when you put that in here, what do you get? Sine of 2 times, when you have 2 pi over lambda times lambda, what's going to happen? Let's just focus on the sign, right? 2 times 2 pi over lambda times lambda, the lambdas cancel, and this is like doing sine of 4 pi. Well, sine of 4 pi is 0. That's good. This whole thing cancels, and then you just have k lambda to worry about. Now, we could, if we wanted to, say k lambda is 2 pi, put it here, but we prefer to write the equation a different way, so I'm not really going to use the fact that k lambda is 2 pi just yet. I'm going to take this k, multiply it by this k, and then I'm going to say 1/4 mu a squared, and then this k times this k gives you k squared, v squared, lambda. Then I'm going to use the fact that v was equal to omega over k, right? So kv is going to equal omega, right? And then so kv is omega, so we can kind of simplify this and just say this is omega squared, right? So we can get rid of 2 variables and just have 1 variable in there. So kinetic energy is going to be 1/4 mu a squared omega squared lambda. This is the equation that is usually written for the kinetic energy of a traveling wave. It's usually expressed this way. So let's see what the characteristics is here. The greater the mass density of the string or the spring that the wave is traveling in, the more mass it will have, and therefore the more kinetic energy. The omega is related to its frequency, remember, so the greater it's propagating, the faster it's propagating up and down, the kinetic energy is greater. So if you double the frequency, you quadruple the kinetic energy, right? You double the frequency, you quadruple. So it's a squared relationship. This is the wavelength. So the kinetic energy is proportional to the wavelength, but not the wavelength squared, right? So it's only proportional to wavelength. Now, the other thing that's interesting is the kinetic energy is proportional to amplitude squared. So if you double the amplitude of a wave, you quadruple its kinetic energy. So a wave that is bigger in the vertical direction packs more kinetic energy. Okay? Let's see if the units of this works out. It's always good to do some unit analysis, right? If it all works out, it should give us units of joules, right? So a quarter doesn't have units, so let's focus on the rest of the material here. Mu is units of kilogram per meter, okay? This one is meter squared because it's amplitude, okay? Omega is what? It's rads per second, but rad is not really a unit, so it's a unitless unit, so it's basically 1 over second squared. So 1 over second quantity squared. This is rads per second, but I'm ignoring the rads. And then you have another unit of meter. So let's see how it's all going to work out. So this one should have units of joules, right? So let's see here, you have a kilogram, and then one of the meters is going to cancel one of the meters. So you're going to have then kilogram meter, right? And then this is going to give you per second squared, kilogram meter, because one of the meters canceled, per second squared times a meter. Well, smile appears on my face because you see it works out. Kilogram meter per second squared is actually a Newton. Newton times meter is a joule. So it actually has the correct units, but interestingly, the amplitude is squared, but the wavelength is not, you see. The kinetic energy should also be equal to the potential energy that the wave has over one wavelength. Remember, the kinetic energy is maximum when the wave is traveling like this way. Remember that when a portion of the wave reaches the middle, right, it's moving the fastest. So when this portion reaches here, it's also moving the fastest. At the middle is when they're moving the fastest. At the end is when they have more potential energy due to their position, right? But over one wavelength, okay, the potential energy should equal to the kinetic energy because we're assuming kinetic energy, potential energy conservation. This is very similar to what we said for the springs, right? When you have a spring like this, and then I stretch it, when I stretch it, it has the most potential energy, half Ka squared, right? When it's moving through the center, it has the most kinetic energy. Kinetic energy, half mv max squared, right? So if I want to know the sum of the kinetic energy and the potential energy at any point, I can just say U plus K is equal to what? The maximum potential energy that's stored at the end. So then that's equal to half Ka squared, right? So you make a general equation like that. The maximum potential energy at the ends. This is the velocity at any point along the path. And then this is the potential energy at any point, right? So if I want to know the maximum velocity here at the middle, then I set this equal to 0, and then V max is going to equal Ka squared over m square root, right? So a lot of things that the spring has are similar to the way that waves behave, okay? And then if I want to know the general equation, I'm going to say Kx squared plus mv squared is equal to Ka squared. And then that gives me the velocity at any point on the path. So V is equal to Ka squared minus Kx squared over m square root. This gives you the velocity at any point along the path. The omegas are going to cancel, and we're going to say y squared plus Vy over omega quantity squared is equal to a squared sine squared plus a squared cosine squared, right? And then since sine squared plus cosine squared is 1, we notice that this is just equal to 1 like that. And then we could say y squared plus Vy squared over omega squared is equal to a squared. So this is going to be similar to the equation that I wrote up for the springs. Then all I need to do is be able to know the amplitude. Then I take this y and I subtract. And then this tells me what the V sub y is for any value of y, right? So what would be the maximum value of V sub y? Well, that would occur when y is 0, right? When y is 0, then what would happen? V sub y would equal omega a. So that would be the maximum value of V sub y. Well, it actually makes sense because V sub y is negative a omega. It's whatever is in front of the cosine, right? So we know that that's the maximum amplitude, and even from here we can say when y is 0, that is also the same absolute amplitude. So basically we're getting rid of the t in this equation, and we're just relating v sub y with y, right? Then we can kind of follow up with this equation and do some more stuff with it. Then I can multiply everything by half m. So half m omega squared y squared plus half m v sub y squared is half m omega squared a squared, right? So then what's going to happen? Well, for the wave in the string, the mass is its linear mass density times its wavelength. So we can write it as half mu lambda omega squared y squared plus half mu lambda v sub y squared. That's equal to half mu lambda omega squared a squared. So basically this replaces the potential energy kinetic energy equation for the springs. We have half kx squared plus half mv squared is equal to half ka squared. So half kx squared, y replaces x, that's the vertical position of the wave in the string. K is replaced by mu lambda omega squared, right? So this one is like the spring constant of the spring. This will be the spring constant of the string. B mu lambda, well that one is pretty straightforward. That's just the mass of the wave in the complete wavelength. And then this will be the K again. So mu lambda omega squared, and then the amplitude, this is the amplitude squared. Let's see if the units of this works out. The spring constant of the spring has units of Newton per meter. Does this have units of Newton per meter? Well, you have here mu is equal to kilogram per meter. This is equal to meter, and then this is equal to 1 over second squared. 1 over second squared, because remember omega is rads per second. So what's going to happen? Well, you're going to have kilogram, meter is going to cancel, 1 over second squared, right? How can we get Newton meter out of that? Well, I can multiply this by a meter, and then I can divide by a meter, right? Why am I doing that? Well, because kilogram meter per second squared is a Newton. So, and then this becomes Newton times 1 over meter, Newton over meter. So mu lambda omega squared is the spring constant of the spring that is pulling the wave back to the middle, right? So it's acting like its spring constant. So now we can say, what does this express? This expresses the instantaneous potential energy of a point along the wave. This represents its instantaneous kinetic energy, and this represents the total energy, right? If I average this out over one wave, this is, if I average this, and then average this, what should the average energy be? Well, the total average energy should be 1/2 mu lambda. So E total, since the total is constant, its average value is equal to its instantaneous value, right? So this is instantaneous total energy, and its average is also the same. So the E total average, I can just put a bar over it like this, is 1/2 mu lambda omega squared A squared. Now, previously we found out that the average kinetic energy over one cycle, right, lambda, right? So how did we do that? Well, we integrated it over one cycle, and we did all that technique, and we derived this. That's the average value of the instantaneous kinetic energy over one cycle. We got quarter. Well, how do we do this? We don't have to do the integration thing all over again. We can just say the average potential energy function should equal what? Well, this minus this. The total energy is basically 1/2. The average kinetic energy is half of that. So the potential energy must equal, the average potential energy must equal this. Potential energy average, 1/4 mu omega squared A squared lambda. Because if you add a quarter to a quarter, then you're going to get 1/2 mu lambda omega squared A squared, right? So now we have derived the total energy, instantaneous, the average, and the average kinetic energy, the average potential energy, and they're equal to each other, you see? Now we can make a derivation for the average power of the wave. The power of the wave is going to be its average energy over the period, because power is joules per second, and that gives you watts. So if I divide this over the period, 1/2 mu lambda omega squared A squared divided by the period, we're going to get the average power. Well, remember that omega and the period are related. Omega is equal to 2 pi over the period. So we could either get rid of the period in the equation or get rid of the omega. Well, since we wrote the energy equation in terms of omega, we might as well write the power equation in terms of omega too. We can say the period is equal to 2 pi over omega, right? and then we can put that into here. We have, and then you're gonna get an extra 2 pi at the bottom, mu lambda, and then you're gonna get omega cubed amplitude squared. Usually it is not written this way. We can do something else to get rid of one of the other variables. Over here, we can notice that velocity of the wave is equal to its wavelength times its frequency, right? This is true for any wave. And then we can say wavelength frequency is 1 over its period. So we can immediately notice here that the wavelength divided by its period is equal to its velocity. So instead of getting rid of the period and expressing it as 2 pi over omega, we can say wavelength over period is v, so the power average is equal to 1/2 mu times its velocity times omega squared a squared. So depending on what variables are given to you, if you want to use this form of the power equation, you can, if you know the omega and the mu and the lambda and the a squared. But this is the typical form that is written for us. So what we can see here is that the average power depends on its velocity, its linear mass density. The faster it's moving, if you double the velocity, you're going to double the power. If you double the linear mass density, you're going to double the power. But if you double the frequency and the amplitude, if you double the frequency, you're going to quadruple the power. If you double the amplitude, you're going to quadruple the power. So this is the official way that the power equation of a wave is written. Okay? So now you can see how we derived it, and how we derived the energy equation, and how we got their average values. Thank you very much.